Man's conquest of the sky has always depended on the precise crafting of aircraft components. From Leonardo da Vinci's first vision of flight to the Wright brothers yearning to make a wooden eagle soar, the propeller has provided the means to make these dreams a reality. Although originally handcrafted from wood, today's propellers are made from either high-strength aluminum alloy forgings or space-age composites, providing the strength for today's more powerful engines. Companies like Hartzell, propeller manufacturers since 1917, continue to lead the way in propeller design. Today's designs are a long way from the first hand-carved black walnut propellers. With the need for stronger and lighter propellers, Hartzell is leading the industry with their lightweight carbon composite blades. Periodically, propellers need to be overhauled. This increases safety, prolongs the propeller's life, and improves its function and operation. The overhaul process consists of periodic disassembly, inspection, reconditioning, and reassembly of the propeller. The overhaul interval is generally based on hours of service, but a calendar limit also applies.
It's been a year since the last annual, and it was in September. We got to the end of this month, so we need to take it down and start the annual on it. Actually, they're going to pull the DME and take that over to Bob's and get that taken care of while it's down, and they're going to check the propeller at the same time.
Aircraft propeller overhaul facilities are FAA-approved repair stations. This ensures that only certified and qualified technicians are working on the propellers. Since proper overhaul is so crucial to the effectiveness and safety of the propeller, each propeller is issued a series of inspection forms. This ensures that each step of the process is carried out to completion. Before each propeller is disassembled, a pre-dimensional checkup is performed on each blade. These checks are to determine whether the width and thickness of the blades meets the minimum specifications per the manufacturer. They are done from the center line of the hub out and at certain blade stations depending on the blade make and model. After they are measured, they are compared against the manufacturer's tolerances to make sure they stay within the minimums. At that point, the propeller can be further disassembled, and each part is visually inspected during this disassembly process. After the parts have been disassembled and all the grease and contaminants removed, they are thoroughly cleaned before each inspection process to follow. Any painted surfaces on the propeller blades are removed with a medium blast. The ferrous metal parts are then magnaflux inspected to determine whether they have any cracks or flaws. They are inspected under a black light. The non-ferrous metals or aluminum parts are dye penetrant inspected. A red dye is applied to each part and allowed to dwell. They are rinsed off, allowed to dry. From there, a white developer is placed on the blade that will indicate any cracks or flaws in the material. Blade shanks are placed on an optical comparator. This projects a shadow or image of the blade shank into the screen with a template provided by the manufacturer. The outline has to fall within specific guidelines. If it fails to fall within these lines, it is removed from service. Blade shanks are also eddy current inspected. Eddy current determines if there are any cracks or subsurface defects in the material that dye penetrant inspection cannot pick up. An optical magnifier is used to look for any defects or flaws not made visible by the dye penetrant inspection. Each component of the propeller is then dimensionally checked using telescopic gauges, micrometers, and calipers. As each component is measured, if it is determined to be unairworthy, it will be removed from service. As these components are checked, they are compared against the manufacturer's dimensions and then recorded. Here are some parts that have failed due to lack of preventative maintenance. This was from a blade nick in the leading edge of a blade. This blade cracked and separated on takeoff. This is a blade retention ferrule, responsible for retaining the blade in the hub assembly. It is almost cracked completely around. This is a blade race that was cracked through. These parts were removed from working propellers. These are the blade thrust rings of a Hamilton standard propeller. These rings are placed on the blade during the manufacturing process as the blade butt is swedged out. All nicks and flaws in the blade ring have to be removed by a grinding process. This is done on the blade itself. If the rings go below minimum dimensions, the entire blade is no longer airworthy. The blade bushing is then reinstalled in the propeller blade butt. After that, the rings are secured to ensure they don't damage the blade shank. Any pre-straightening or forming of the blades is done in a hydraulic press. Everything is done in the cold condition. Nothing is heated. During the straightening process, the alignment is checked and the blade is adjusted if necessary. After the blade has been straightened, all blade angles have to be checked to make sure they fall within the manufacturer's tolerances. Then the blade track is checked to determine the track between each blade. When the blades have been straightened and the angles have been set, They are sent to a grinding booth to be reworked. Any flaws, nicks, or scratches in the blades are removed. At that point, the blades are again dimensionally checked to ensure that the blades were not filed or ground under minimum specifications. Blade angles are again checked to make sure the grinding process did not remove the blade angle. Once the angle straightening process is complete, the blades are dipped in an iodine tank for corrosion protection. They're then coated with an acid wash primer. After the primer is dry, a Pauline paint is applied to the blades. After the paint has been applied, the blades are removed and placed in an oven and baked for 3 hours to ensure durability of the paint. The pre-assembly process involves installing studs in the hub assembly. The standoff is checked with a gauge. Then Loctite or epoxies are applied to the studs. Prior to installing the blade races, an epoxy is applied to the blade shank area. This creates a bedding for the race. It fills any voids and flaws and also glues the race to the blade. Lubricant is added to the blade race, preparing it for the ball bearings. Races are checked to ensure a proper match. They come in a set and are split. Any excess grease is removed. The blades are then installed in the hub assembly. The hub median surfaces are thoroughly cleaned, and an RTV sealant is added, preventing any moisture from entering the hub. The two hub halves are aligned and installed. Bolts are installed and properly torqued. The pitch change rod is installed and properly torqued. The blades are then neutralized, and blade angles will again be checked at the setup stations to ensure they fall within 0.2 of a degree from each other. If not, they will have to be corrected. The blade track is again checked at this point. All inspections and dimensional checks that are done prior to this will be checked off on an inspection list. This ensures that each process has been done up to this point. The dome housing for the feathering spring is assembled. The spring is compressed and compacted into the dome assembly. The piston nut is properly torqued. The installation tool for the spring dome assembly is prepared. The dome is then installed. The feathering and latch stops are installed. The low pit stop is then installed. A compressed air charge is placed in the propeller to check for the proper operation, which will simulate governor boost oil pressure. When the assembly process is completed, a static balance of the propeller is done on both a vertical and horizontal position. If any weight correction is needed, weights will be added per the manufacturer's specifications. A more elaborate form of balancing is the dynamic balancing. This is done on the aircraft in a running condition. Dynamic balancing incorporates a spinner, the bulkhead, starter ring gear, and engine components. They all need to balance as one unit. Most balancers use the Chadwick-Helmuth dynamic balancer. With aircraft running, the propeller is strobed and checked for proper balance. To correct improper balance, weights are added. The operator determines the amount of weight and the location of the weight to be installed. The weight is then installed per the manufacturer's instructions. Weight locations are determined by the propeller manufacturer, engine manufacturer, or Chadwick-Helmuth themselves. After the weight has been installed, a secondary run is performed to ensure the proper location and the proper weight has been installed. If it falls within the limits, the balance is complete. Dynamic balancing can be performed on a single-engine trainer, all the way up to a corporate executive class aircraft. This balance is being done on a turbine engine using a more modern balancer analyzer. During the rigging process, proper clearances and fit are checked. A proper dynamic balance is performed to ensure that all the components of the aircraft propeller and engine are operating together in a balanced condition. This will limit the extent of wear on the propeller, engine, and airframe components. An initial run to determine the amount of weight and location of the weight is done. Once that is determined, if any weight correction is needed, it will be done. If not, it will be noted, logged, and tagged. This completes the overhaul process of a typical aircraft propeller. After completion, you can be sure the propeller is airworthy.